Welcome everybody to the British Astronomical Association Hydrogen Line subgroup meeting. It's wonderful to see you all again, and I hope you're remaining well in this sort of winter season from all these colds, etc. But it's always brilliant to see you every time we meet up and to hear how things are progressing where you are. We're very lucky tonight. We've got Heather Nichols, who's going to talk to us about designing horn antennae for hydrogen line work. So I'm certainly very excited to hear this talk, because it's something I'm hoping to build. In fact, I've gone a step further than that. I've actually had some galvanized steel plate arrive, so I've got the kit ready to do it. So I just now need to find out how I'm going to do it, which hopefully after Heather's talk tonight I'll have a bit of a better idea where to go next. So are you happy to start us off, Heather? Oh, you are muted at the moment.
Yeah. I'm trying to work out how to share a screen. It's always different every single machine I use.
Oh, that's fine.
Let's try that.
Yep, we can see.
Sharing?
Yep, we can see your presentation there. At the moment, we've
Okay.
got it looks like a PDF file with little pictures on the left and a big one in the middle.
Right. Okay. So this isn't my presentation. This is somebody else's. This today is going to be rather an exercise in plagiarism, because I haven't written much, because a lot of people have done a lot of better job than I have. So my apologies to people who I've used their diagrams. We'll start with this one. So the problem we're trying to overcome is to get basically horizontal signals or vertical signals. Let me find a better one, that one. So signals are coming in from the left, and because they're coming from a long way away, in our case, they are going to be, to all intents and purposes, horizontal and parallel. They're reflecting off a mirror, and they're being focused to a point. And what we want to do is we want to put some sort of sensor, what we call the feed, at this point. My apologies for keep looking away. The diagram's on a different screen to the one that you're all on. So the first challenge we have is, what can we put there that will give us a reasonable signal? And the way we look at these things is this type of diagram, which this is the traditional coffee can feed. I guess people are familiar with that. Do I have a picture of it somewhere? No. Oh yeah, there we go. So this is a bit of an old coffee container with basically it forms a little bit of a cup or a tube with a flat end to it. And simplistically, the way it works is the signal goes down the tube, reflects off the bit of metal at the back of it, the floor of the tube, and comes forward. And because you've got two waves, they will interact, one coming forward, the other one going backwards, obviously reflecting. They will interact, and what you'll get is highs and peaks and troughs, where you get constructive interference and destructive interference. So that's kind of what we're doing, and we're going to try and make this as suitable for our frequency as we can get. And we're also going to try and make it as suitable as we can for our dish. And those two things end up defining how the thing's going to look. So back to this picture, you can see that what we have defined here, the red bit, I don't know how quickly this is updating for you, by the way. So what we're seeing here is that some of the signal will get into our sensing bit, in the middle from outside of the dish. And that's what's marked in this red spillover marked at the top of the diagram. So what we want to do is we want to avoid that if we can, because that's obviously signal that isn't coming from wherever we're pointing our dish. And what we want to do is get almost to the edge, but not quite, so that we're getting as much of the signal from the dish as we can. So going back to these pretty diagrams, this thing shows us in this circular diagram, left-hand side, top left-hand side, it shows us what the beam pattern is. I'm not sure if everyone's familiar with beam patterns, but basically what it's saying here is that the center, the focus point, is right in the middle of the center circle. And then you've got right in front of the sensor, the very left-hand most. Can you see my cursor, by the way? I don't know. Can anyone see the? Do you see the cursor on the screen?
Yes, we can.
Yeah, we can see it.
Yeah. Okay, great. Okay, so.
Sorry, your other question.
Where,
your slides update quite quickly, so don't worry about that.
Okay, cool. So this point is pointing straight forward, and you can see this is the point of maximum gain, which most software defines as a reference of 0 dB. So that's saying that everything is measured relative to this maximum point. Other pieces of software will do things in a different way, but basically the further it is from the center, the higher the gain. And so you can see that pointing straight in front of it, it's the highest gain. Then you've got this point up here, on the red line, you've got it going down to minus 10 dB, so that's a tenth of the signal. So it's still seeing some signal there, but not very much. If we go and look at this, say this point here, which is something like minus 15 dB, so that's going to be 20 or 30, 1/20th or 1/30th of the signal. Everyone familiar with dBs, I hope? Okay, so that means even straight up away at right angles to the center of the sensor, we're still seeing some signal. And what we want to do, of course, is basically we want this pattern to be something this shape, so a segment that is just covering our dish. So our ideal would be something that has a beam pattern of this this line around the dish and then this line. So if we've got any beam pattern greater than 0 around here, then it's going to be receiving spillover. It's not going to be doing a good job of receiving what we want. Now, unfortunately, that is extremely difficult to do. And if we look at this one, here we can see that, again, we've got our feed point, our sensor here, and this is its beam pattern, so it's a sort of cardioid shape. So it's looking good straight on. It's got a maximum gain into the middle of our dish, which is great. But you can see that there's a bit of gain around this section here that's marked in red. And this is obviously receiving signals that are not on the dish. So it's quite good in that the gain is good all the way around here and all the way around here, but it's not brilliant. So let's go back to our cantenna. We can see that if we just put the cantenna on its own without a dish, it will be receiving a lot of stuff from all over the place. Not bad straight ahead, so that's why it actually does work for those of you who've used a cantenna. But it's still receiving signals from way over here, quite a lot of signals from even at right angles to the signals. So when you can visualize this, that signals coming in from all over the show, left, right, up, down, anywhere, will be coming into this antenna, not just the ones that we expect to come from the front of the system, from the antenna. So that kind of sets the scene. We could just put a cantenna on a feed on a dish, or we could just point the cantenna in the general direction of whatever we want to look at. And it will work because it's got some directionality, but it'll also be picking up lots of stuff, so it won't be very much gain in our favoured direction. So then, obviously, we want to do better than that. And there are various ways of doing it. I'm going to have to go look for, I think I decided that page 6. Okay, that was cantenna. This document. Okay, there we go. There's another version. This is one of the V4 MA ones, which I think Andrew was looking at. He was looking with which. This is a thing with the Kumar feed, which is basically the cantenna with another ring around it at various calculated distances away from that centre point. So you can see here that it's beginning to look quite good. It's got a little bit of what we call side lobes, these tails and so on going on here. But basically, this pattern is pretty good. So that's why we have this, what we call the Kumar choke, which is effectively just stopping signals from coming in from the sides. So if you remember, with just the cantenna, without the choke, this thing came all the way around here, up to sort of minus 12 or so. But with this one, it's cut off a lot of that, and you're just looking mostly forward. And if you've got a dish that's sort of starting up here, then as it comes down, you can see that it's pretty good. It's going to do a good job. But it's only going to do a good job if that pattern fits in our into this. So if you put this too far away, if you put it right over here on the left of the diagram, you're going to be seeing kind of stuff up here. Similarly, if you put the feed right over here, it's only going to be seeing this bit of the dish. So you can see that pattern, the radiation pattern of the feed, is quite dependent on where it sits inside the dish. And obviously you want it to be sitting at the focal point. So now you see why I came back to this picture here right at the very start. So this is the way a dish is defined. So any parabolic dish will have what they call the F over D ratio. F is the focal distance, D is the diameter of the dish. So if you've got a dish with an F over D of 0.25, say, you will need to have a very different type of beam pattern to if it's 0.75, where the focus point will be further away from the centre of the dish, and therefore you can have a different beam pattern in order to completely illuminate your dish. Did that make sense to everyone? Hopefully it did. Okay. So this is why we start to see pictures. I don't know whether we've got any here. Okay. So there we go. So when we have this feed, this is the 1296, but it's close enough for our purposes anyway. And you can see that he then does a different plot where he adjusts the F over D, and you can see that if the FOD changes, then his plot will change because he'll be seeing different parts of the dish. And there's various other ones here which, okay, that's gone too far, sorry. So the whole of the design principles of what we've got to do here are getting the feed with this choke, if we're going to use a Kumar choke, which is the single ring. There are others which I might be able to get this one to show us. No, okay. I'll go to simulator in a minute anyway. Right, okay. I'll talk a little bit about Waveguide. Waveguide theory is pretty much a whole degree year's worth of studies, so I'm not going to go into waveguides in any detail at all. But basically, a waveguide is any circular or rectangular piece of metal. So it's basically a tube, and its size is such that the wavelengths you're interested in will propagate down it as an EM wave. Excuse me a second. In such a way that it won't just get confused or reflect off different surfaces and so on. And the way it does that is quite complex. I don't know if anyone's familiar with skin depth for various things like audio and that sort of thing. Well, the skin depth is really defined in our case by the smoothness of the metal. So if you've got a nice smooth surface, then the wave will propagate, the EM wave will propagate down it as if it was a plane of metal. But if it's a rough surface, then it won't do that because it's going to be going round and up and down and so on. So this is one of the reasons why, although people talk about dishes with having a defect level, and typically people talk about 1/10 of a wavelength of maximum defect in a dish, but that's true because you're only getting reflections. But on a waveguide, you actually need much better than that. So a waveguide at 10 gigahertz in theory could have, which is 3 centimeters wavelength, you could have 0.3 centimeters, 3 millimeters of defect in the dish, and you'd still be absolutely fine. But if you try doing that in a waveguide, you're absolutely going to screw it up. So waveguides need to be smooth so that you get the correct skin effects on the propagation of the metal. Now, one nice thing about waveguide is that although it'll transmit frequencies higher than its fundamental frequency, it won't transmit any frequencies lower than that. So it means that it acts as a high-pass filter, which from a microwave point of view is absolutely brilliant because we've all got FM stations and BBC and all the rest of it all floating around in the atmosphere. But as long as we choose our waveguide to be slightly lower than the frequency we're interested in this case, 1420, but not too much lower, then it will cut off all these nasty radio signals that could mess up our stuff. And we'll only see signals from that frequency and above. And its propagation in the way we want to use them anyway, means that if you go up a few multiples of wavelengths, it also starts to attenuate there as well. So the bottom line of all of this is that you have to make your sizes correct for a little bit lower than your frequency that you're actually interested in, so that it will propagate nicely. It won't be attenuated, but it'll also be in the highest gain part of the range of the waveguide. So the simplest way of looking at it is that it forms a half a sine wave across the longest axis of a rectangular waveguide. I did have some pictures. Unfortunately, they're not awfully. I don't think I'll bother showing them because they're a bit confused. But basically, there are different modes. People talk about the TE modes and TEM modes and so on. We're only really interested in the fundamental, which is basically one wavelength across, which is why if you look at 10 gigahertz for your satellite dish, for instance, you've got a waveguide which is about 20 mil across, which is, it's circular, so the calculation becomes slightly different. But when you start coming down to our stuff in the 1 or 2 gigahertz range, it becomes 10 times the size. So we're looking at things that are 100 plus millimeters across, and say at 10 gig, you're looking at things that are sort of 20 mil across. So it's this order of magnitude that we're looking at. We use circular for most things to do with the hydrogen line. It doesn't really matter. We could use the rectangular waveguide, and those of you who've used horns, basically a horn is just a converter from a large aperture down to a waveguide of the right aperture, and then once the signal has got into the waveguide, it'll propagate down that waveguide as long as the waveguide is, and it's very low loss because it's actually effectively it's reflecting off a good surface within the waveguide. So waveguide can be very long. You can have meters of waveguide if you want, whereas if you put meters of coax in, even at our frequencies, you'll start to get losses very, very quickly because coax is a lossy medium, whereas waveguide is very low loss. But eventually, once you've gone into the waveguide, you want to actually convert it, as we've said, into one of these probes. Let's go back to my antenna. So this is the waveguide, the CAN, and it will just propagate down through there. But because we want to get a nice strong signal, as I've said before, we will reflect it off the back, and we'll get reinforcement and cancellation of the waves at the best point. And you can calculate that. The wave is pretty much travelling at sea, so it is actually the round trip has to be half a wavelength. I think that's right. Anyway, this can all be calculated for you, and plenty of people have done these calculations online for our types of antennas. So now when you change frequency, obviously because you're changing the wavelength, that means you've got to move that point. So the distance of that point from the back of the waveguide is quite critical, as long as your waveguide is acting like waveguide. Now, the next question you have would be, how far in do I put it? And again, there are mathematical models of how far to put it in. The problem is that the wave is interacting with the sensor, the little bit of wire that you've stuck up into the tube. And also, the wave is propagating down this thing in quite an unusual way. As I've said, it basically, if you remember what a wobble board is, that's the best way I could think of describing it. It's wobbling its way down in a sine wave, but as a plane. So you've got an E plane and an H plane, and it's kind of wobbling its way down. It's very difficult to visualize. You can find some good YouTube demos of it if you want to try and understand it more. But basically, it means that the back to front position shouldn't change, but the depth you insert it into the tube, into the waveguide, might change depending on what it's made of. And also you have to remember that the waveguide is being sensed relative to its inner surface. So if you've got, as I know some of us have done, we've made the sensor, the feed point, out of some material, and then we've tried to coat it to make it conductive. You need to have your ground point, which would be the outside of your SMA connector or whatever. You need to have that physically connected to the inner of the waveguide, because you shouldn't get any signals on the outer. But then the path, if you're just connecting to the outer of the waveguide, the path for the signal will be all the way down the waveguide, round the top and all the way back in. So it's quite critical that that is correctly done. And all the models that you'll see assume actually that you're making this stuff out of perfect conductors. If you start to do anything else, like copper or aluminium, behaviour isn't going to be quite as good, and you're going to need to start to consider how the transition is made. So, okay, so there we are. We've looked at the fact that you have to match the F/D ratio of your dish to the Kumar feed, or whatever feed you happen to be using, so that we can get the beam pattern to look at the whole of the dish, but not more than the dish. We've looked at the size of the waveguide, which we're trying to feed this thing into, which is defined by our parameters of the frequency we're trying to look at. And we've looked at the way we can get a signal out of a waveguide into a bit of coax via a bit of wire, as we see in the antenna. So the key takeaways here from discussions we've had in the past. The first is that the Kumar feed, or the extra rings we're putting around the waveguide, are only really helping us with respect to our dish. They're not really helping us with anything else. So when we simulate a lot of these things, we really should be simulating with the feed there, but remembering that the pattern we get is not going to be the signal we get unless it's matched to the dish. So that's our first kind of takeaway, I guess, from this. The next thing is going to be the impedance. And I know this is, again, something Andrew's done a lot of measurements for. I'll step back slightly. The beam width, so the frequency width, bandwidth of the antenna, or the coax, or the waveguide, is dependent on the dimensions of the waveguide. So as I said, we're going to be working in the lower region of the waveguide. But also, of course, it depends on us matching our frequency to the position of that little sensor, the little wire that sticks up in the picture there. And the thickness of that bit of wire makes a difference, because if it's thicker, it will be interacting with different points in the wavelength. So if you imagine that the wave is going down, reflecting off the back and coming back again, it will be reflecting off at slightly different distances if you decided to be working on the nearer side of that little wire, or the further side. So some people actually do put little cylinders in, because that gives you a much wider bandwidth. That shouldn't help us, because we're only really interested in a very narrow bandwidth. But again, it's got to be non-zero, obviously, because it's got to be made of metal. But that thickness takes us on to this consideration of impedance matching. We know that our coax is going to be 50 ohm, presumably, if we're all using 50 ohm system, or 75 ohm if we want to use different impedances. But again, this is part of our design criteria. And the way we transition into that 50 ohm cable, obviously it's by this little probe that comes out of the bottom of the connector we're using, the N-type or SMA or whatever. So this is all quite critical to how we do the transition. So we've looked at what we're trying to achieve here. I've tried to avoid getting too mathematical, partly because I don't understand the math, and partly because it's a thing that a lot of people have done already and done quite good designs for. So as long as you can find the F/D of your dish, and as long as you can calculate where the center of the reflection is, so that for an offset dish, that would be where the offset is. For a complete parabolic dish, that will be the focal point as calculated by the F/D. Then you should be able to get a design offline that will match all that together. So we've gone through all of that. The next thing we want to look at is how to simulate this. Simulation is basically, fundamentally, it's solving Maxwell's equations on a grid basis for lots and lots of what they call cells, but basically it's a grid. So if I go back to my little picture I've done here, so this is a program called CST Studio, and it's I don't know how many thousands. It's a lot of thousands to buy, but there is a student edition, and they explicitly say that if you're a hobbyist or doing this for no commercial reasons, as most of us are, then you're quite okay to use the student licenses. It's a professional package. I forget the numbers. I think 25 grand in UK terms to buy a full license. The trouble you have is that the simulator is limited for the student license. So it's a good way to learn, but it does mean that you can't do everything in one go. And I created a model of the horn, the Kumar feed horn that we were discussing last time, and it just won't simulate it. It says normally it wants to take a mesh size of 1/10 of a wavelength. I did that, and it said, sorry, you're trying to do too many mesh elements for the license. So I reduced the number of mesh elements, and then it ran and it said you haven't got enough mesh elements to get a good result. So it kind of catch-22. But you might remember what I said earlier, that you can have long pieces of waveguide. The distance from the front of the waveguide nearest to the dish and where you put that sense point could be a meter. You don't really want to do that because it's, physically it's a silly thing to do, to try and put a meter sized thing on your dish. But for a simulation point of view, once the signal is simulated getting into the waveguide, then you could say, well, I now know what my signal looks like. It's getting into the waveguide, so I know all the beam pattern part of it. And so you could design all the front part, the Kumar feed, this ring, the F/D, all that can go into just designing the very front of it. And then you can say, right, I know how that beam pattern works. And then you can go down and say, right, I'll just assume it's all the signal has got into my waveguide. And then you can start playing around with this feed point and the probe distance and everything in a completely separate simulation. So one, you're feeding a signal in from outside coming into your feed with its Kumar choke or whatever, and then you do a completely second simulation to see how well you can simulate coming out into the coax. So, to be clear about it, I haven't done that yet. I got as far as doing the whole simulation, and it wouldn't do it. As I said, it just, the license wouldn't work. I have since then discovered that if you ask CST very nicely, they will give you a 7-day or 1 month license, full license, if you have a particular problem that you'd like to solve. They are quite amateur radio friendly, because they know that a lot of amateur radio people end up working in a business where they might end up buying the thing, similar to the way Apple do business, that they give almost free apples to students and universities so that they get them hooked early. So anyway, CST are quite amenable to that. And what I might do is go and approach them and say, we're trying to understand this kind of thing in this group. Maybe we could have a license that the group could play with for a week or two. But anyway, so what are the fundamentals of how we do a simulation? So I'll very quickly go through CST. I'll close this thing here. Don't want to save it. So we want to create a new thing to simulate. We'll do it from a template. New template. My machine, by the way, is a 20-core i9 running at 4.4 gigs, so it isn't the fastest piece of software, but you'll see what, when we get into it. But you do want quite a good machine. It is essentially a non-parallel process, so there's a lot that these simulation programs struggle with because of the way they need to solve Maxwell's equations. But so we're doing a microwave system, we're doing an antenna. Hopefully the Zoom is keeping up. Teams is keeping up. We're going to do a waveguide antenna, and we're going to simulate everything in the time domain, because that's what we're interested in. We're interested in how well the beam patterns form for these things. You're going to create a project, so you want to set all the kind of parameters that you're going to want to simulate. In our case, we're going to simulate, I'm going to say, from 1 gig to 2 gig. We don't particularly want to worry about I would advise, if you do start playing with this, that the best way to learn it is to pick up some of the tutorials and start playing with all of these type of things to get a feel for how they go. But basically, this is an example of the type of thing we might create, and it's telling us what we're doing. And so then it will create us a blank thing eventually. So once it's done this, the first thing we want to do is we want to actually create a physical model of our system. And okay, so we go up to modeling, this menu item top left, and we've now basically got a 3D drawing program. So I'm going to select this one, which is the cylinder, and with the cursor somewhere in this this greyish area in the middle, I'm going to press escape. And what that does is it gives us, rather than giving us a graphical drawing thing, it will give us a thing to draw by having the parameters. So if we knew our parameters, unfortunately I haven't got them written down, but let's just say we're going to create a waveguide with an outer radius of 160 millimeters, an inner radius of 159.1 millimeters. So this is basically going to be a fairly thin tube. we'll have it starting with the centre at 0, 0, which is the midpoint of our plane, and we're going to extend out from that. We're going to start at 0, so actually on the plane, and we're going to extend out by, let's say, 100 millimeters. Actually, no, let's say 300 millimeters to make it. So we're going to draw this, and we need to tell it what material. PEC is perfect electrical conductor, so that's a theoretical thing, which is just kind of obvious, but we want to make it out of copper, say, so we'll load material from the library. We've got a big library in CST, various types of copper. We'll use annealed copper. I don't even know what it is, but let's use it anyway. And then we hit OK, and there it's drawn it for us. We've got the mouse wheel can zoom in and out, and we've got we can use the cursor left button, drag and drop to zoom in on bits of it, or we can just use the mouse button to zoom in and out. And that's basically what you do. If you wanted to then generate the back plane, if we were going to do our feed point, we could come along and we could do another cylinder. Again, press escape. This cylinder is going to be the size of the back, so 160. Obviously, it's going to be all of it, so we have an inner radius of 0, so it's just going to be a disc. Centered on 0, 0 again, and we're going between 0 and -1 millimeter, so it's a 1 millimeter thick disc at the back of our device. So if you press Control, you get Control and then left button, and you move the mouse, you can rotate the thing. So yeah, you can see we've created a cylinder with a flat bottom. So that's created our cantenna, for instance. And so the next thing we want to be able to do, once we've created our antenna, and if you want to do the Kumar feed, you'd create another cylinder like this one, but it's like, so another cylinder, but only starting, say, up here, and then another one of these plates, but just going between the outer cylinder and the inner cylinder. So that would create the step kind of Kumar feed. And that would be enough to simulate most of what we want to do here. The simulating waveguide, we would create a tiny little cylinder coming in from the edge. Then we would create a PTFE cylinder so that it breaks into the outer cylinder, and then we'd come away from that as another PTFE cylinder, so another copper cylinder. So now we have an inner solid one and an outer shield one, and that, after a few millimeters, would be simulated as our bit of coax. You could change those PTFE parameters or whatever, or you could, if you could find them, find what a SMA looks like. That's what I did earlier, but so you could put in all the dimensions of an SMA connector as if it was part of the cylinder. But all of this, unfortunately, means that it becomes very hard to do within the student license. So for now, we could just say that we've created this thing and we want to simulate it. Now, this is unfortunately where I am going to not get very far. But first off, if we zoom in on this face, so this is a face of the top of the cylinder. So this is going to be the face that we want to inject signals in from the simulation. So we can zoom on it so that we can see it. We go for simulation, the menu item top left, and we go for picks, which allows us to pick a thing. Drop down and, okay, try again, pick a face, and we highlight in red the face we want to pick by just moving the cursor over it, double left-hand click, and there it's selected that face, so you can just see that it's in red, or dotted red there. And then we can tell it that is our waveguide port. Most waveguides have two ports, of course, the front and the back. And it gives us a lot of information which we don't need to worry about. Again, if you're going to actually do this for real, plenty of tutorials that could take you through what's going on here and so on. But it now creates a plane based on that. So this is the part of the mesh that it is going to be using when it does its Maxwell's wave equation solutions. And oh, excuse me. So that's kind of all the mechanical part of it. If we were going to do this as a feed into a waveguide, what we would have done was created this face to be the outer face of the choke, and then we wouldn't put the back face on. Oops, sorry. This one here, we wouldn't have put that face on. Okay, so I've just got asked to expand the window. Does that work for you? Hopefully it does. Okay. So yeah, you could not have this face, and then you could create this face as another waveguide port 2, and you could then look at the transfer from the front face to the rear face, and that will be it going into the waveguide. So that would be the way you would set it up to do the simulation. Solver, I don't understand much of this, to be honest. Various types of solver settings that you can come up with. You can apply them when you know what they are, and you can hit start. And yeah, okay, so this software is licensed for 100,000 mesh cells, and we've exceeded it. So that's kind of the problem that I face. You can do very simple things with this, but yeah, we can't really get much further from this at the moment. So that's as far as I've got. As I said at the start, I haven't finished the exercise. The next steps would be to get the whole model in 2 parts, as I've said, and then we can look at getting a proper license so that we can simulate the 2 halves of the problem. One, to get all the beam forming things so that we can match our feed to our dish, and then once that's into into waveguide, we can then do a waveguide to coax transition simulation and pull that out into to look at the impedance matching. So that's kind of as far as I've got with the simulation stuff. There are plenty of online tutorials to take you through various things, including the transition and drawing this. There are plenty of ways of doing 3D drawings, as you might imagine. You can actually do it by drawing one half plane of the feed and then rotating it around 360 degrees to get the whole thing, if you wanted to draw it that way. I've just shown you one easy way of doing it with a few cylinders. Yeah, so plenty of examples of how you might do this. when if we come to actually being able to do this. So from this point, having got very frustrated with CST, I had a look at Open EMS, which is a field equation solver designed around the MATLAB or Octave, if you're familiar with that. It's a better solver. It's not limited, so you can solve as much as you like, but it requires that you import the model as basically as a CAD model from something else. I have been told that I can import from a slice model that you might use for your 3D printing. So if you used a package that you could create a 3D print from and then slice it, you can feed that slice model in to OpenEMS, which might be a next step for us to take if we can't use CST. Although I think CST is an overall a better solution. And the other one is to NEC, which is let's find the Waveguide thing. So these were all done in NEC2. It's a much harder program to get to basically to understand how we're putting all these things in. But again, once it's got everything in, it does a good job of solving these things, and it will look at feed point impedances rather more easily than having to do a full simulation of a transition, coax transition. So those are the options going forward. So the other half of the problem, once we've got our simulation, we want to actually go and measure the thing. And as you will have gathered from talking about simulations, everything is done on reference planes. And this is one of the things that, again, I think is not so well understood by people. So I thought I'd quickly, probably teaching Andrew stuff he already knows. But when we use something to measure impedances, we're usually trying to measure using a VNA or something like that, vector network analyzer. And they work on reference planes. So exactly the same way that we have looked at a reference plane, the big red plane that I created on the simulation. So the this red plane here. So VNAs do exactly the same thing. So when you get your VNA and it comes with a calibration kit, the calibration kit is basically you put it on the reference plane that you want to measure. Excuse me a sec. And you then calibrate so the device knows where your reference plane is. And then if it's a waveguide VNA, it would be measuring things at exactly the same place as the simulation has the red plane. If it's more likely to be a coax VNA, then it will measure at the defined plane where you took your calibration points. So usually you put an N-type or a SMA type connector onto your feed horn, and what you need to do is you need to connect that through a bit of coax to your VNA. So unless you put your VNA directly onto the connector, of course, but more likely you're going to have a bit of coax. So in fact, your VNA, you will need to calibrate it at the reference plane, which will be the very end of the coax that you are connecting to the device. So you've got your VNA, then you've got a bit of coax, then you do your calibration with your calibration devices at the end of that bit of coax. And if you've got a very expensive VNA, all the calibration parts will tell you where the reference plane is. And surprisingly, that's actually quite a complicated thing to do, to know where that reference plane is. So anyway, that's the bigger problem that people have with measuring the feed point impedance, is to actually get the reference plane of the VNA right. The way to think about this, of course, is if you were getting a signal coming down your bit of coax, and supposing it was not a very good match, then you will also be getting signals reflecting back the other way down the coax, and you'll be getting these peaks and troughs, just as you would with any form of wave reflecting off something. So if you're measuring the peaks and troughs at the wrong end of the coax, at the VNA end of the coax, then you will get a very different reading to if you measured it at the feed point into your feed, where you aren't getting any peaks and troughs because that's the origin, that's where the signal is coming in from. So it does make a very big difference to how these things are measured by a VNA, which of course it's actually working in reverse. The VNA is inserting signals into your feed and seeing how they come out, or how they're reflected back into the VNA itself. So that's your first problem, or the big problem that I've seen with people when they're measuring one of these things when they made it. The second thing you want to worry about is your beam pattern. And unfortunately, measuring beam patterns, there is no easy answer to this. The best way to do it is to get a little directional Yagi, which would probably be one of, I can't even find it now, but one of these things. Get something like one of those, stand a few 100 feet away from your feet.
We can't see it.
Oh, sorry. Okay, yeah, I think I've probably finished with the this.
Are you holding it up, Heather, or are you showing it?
I've just stopped sharing, and that's the little Yagi feed. I guess various people have seen these things. They're very cheap on eBay. But yes, if you've got a signal generator around about the hydrogen line, and you use it on very low power, feed it into your newly constructed prototype, and then walk around a field quite a long way away from it and look at the signal strength that you're getting, or point a signal source at your feed with one of those little antennas, and then actually measure it from your feed. Either way, you should get the same beam pattern, and you should be able to walk in an arc around your feed and see the beam pattern that you're getting. And then once you know that, you'll know whether it'll match your dish or not. Obviously, if you've got a receiver on that can receive at this frequency, then if you put it on a dish and fire a signal into the dish, you can measure the lobes coming off the side of the dish, and then you could just put the sensor instead of the middle of the dish, and then you'll be able to see what relative signal strength you're getting off the side of the dish. So That way you could tell whether you've matched to the dish. Without the dish, you can tell what the beam pattern is just by walking around the thing at quite a distance. And you could use your VNA with the correct reference plane to decide on your feed point impedance. So that should get you from starting point to an end point without me having told you how to do the bit in the middle. But we'll hopefully leave that to the next stage when I can actually get a simulator to meet our needs. That's it.
Oh. Well, thank you very
Anyone
much
still
indeed. That was brilliant. Thank you very much, Heather. Before we got questions, I'm just going to show a couple of things, as much for the benefit of people who perhaps who are looking in online who may be quite new to this. First of all, Heather was talking about cantenas. So here's a cantenna, roughly the same sort of size that she's talking about. This is an old coffee can, which is why they are very popular. Literally an old coffee can, sort of Costco type of thing. See, it's got a probe sticking down the side on the inside, just from the outside, and basically that is exactly what she's talking about, how to improve on that design. The second thing that she was talking about was a Kuma choke. So here's a piece of aluminium tubing which is doing the same thing as the coffee design, and here's my attempt at making a Kuma choke, this time out of aluminium foil over cardboard. I haven't had a chance to test it yet. And you can see how it's a second ring which is further out. I mean, what Heather might point out, or other people in this group will point out, is that the inner tube should be down to the same plane as the outer tube. When I was doing it, I got it a bit too tight, so I need to loosen that a bit to achieve that. I don't want anybody writing in and saying, "You've got that wrong." And then Heather also mentioned the fact that you could have a rectangular feed, and here's an example of one which is a professionally made one. I didn't make it myself, but that's just to show it's possible to make them so they're not round. In this particular case, it also shows an inner probe which has a big bulbous thing on the end of it, which I believe is to try and broaden the wavelength that this will pick up.
Exactly, that's a very nice example of that. Yeah, I didn't have any examples of that, but that's exactly what I was talking about. The size of the feed is exactly what is going to pick up different bandwidths. Yeah,
well, I thought you discussed it incredibly well. I just thought it would be good just to show a few examples so that people knew what it was you were talking about. So I'd like to hand over to people online for any questions they might have with you. Go for it, guys.
This is Michel speaking. I have a question for you. In the past, I used to be structural engineer, so I was using finite element methodology. I guess it's the same for electromagnetic field. Do you think it would apply to have a when you have cylindrical symmetry, calculation is much easier and faster? I don't know if it applies here, because then you can have much less costly calculation. So I don't know if it's applicable here.
It's applicable for simulating the feed itself and the Kumar choke or whatever. Unfortunately, as you know, where the probe goes in, there's an asymmetry.
Yes.
So yes, it would be very applicable to simulating just the front part, the bit getting it into the waveguide. Yes, definitely, and that's something I have been pointed out by other people. And unfortunately, as I said, I was trying to do the whole thing, so that wouldn't have worked. But doing it in parts, yes, definitely a good idea.
Thank you. Very impressive job.
It would be if I actually got it finished.
Yeah, but I hope you succeed. So you can show us the path to go.
Okay, thank you.
We just need to persuade the BAA to come up with £25,000 to pay for the license for you.
Well, as I said earlier, I think if we ask them nicely, they may give us a license, temporary license. But you never know. I mean, they are very open to people who are clearly not going to try and make money out of it to do these things. So you never know. Yeah, you never know.
By the way, you may know there are open source like FreeCAD that can build a model. I don't know if it interface with your package. You can download the geometry to your package.
As I said, OpenEMS, you can. Oh yeah, sorry, I was just looking to see if this does. OpenEMS, you can import from a slice model. So yes, I use FreeCAD for my 3D printing, and yeah, so that would be Ultimaker and FreeCAD. Between them should generate a good slice model, but I haven't managed to get that to work yet, and I would rather do it in CMS if I can, because it's just a general CST Studio is just a good piece of software once you get it to work, and it's quite well optimized as well. Whereas things like OpenEMS, it's actually a linear solution. So add one cell each way, and you get an exponential increase in processing size. Even things like that little model that I created on the screen earlier, it still takes about 20 minutes to run a full solver on my machine. So yeah, these things aren't fast, but you only need to do them once or twice, and I'm sure Andrew would find it a lot quicker once you've got the model. It would certainly whiz along compared to actually physically building the varieties that Andrew's been doing. So it could be a good step forward if we can get it to work.
Okay, thank you.
Heather, I have a question. Back at the beginning of your presentation, you talked about waveguide skin depth, and you mentioned that that would be, for waveguide, would be substantially less than, sorry, 1/10 of the wavelength. What might it be for 1.4 gigahertz? The reason I ask is that my waveguide is made out of 2 concentric tubes, so there are some small mismatches inside, and I wonder have I exceeded any limits.
Right. It does propagate. We at 10 gig we use 2 tubes and we swage them together. So it doesn't make huge differences. It's really the trouble is the skin effect. I'll just ask Google. It's going to be very small. Copper at 2 microns, 2 micrometers.
Oh, so does that mean that the surface accuracy has to be within 2 microns then for a perfect waveguide?
For a perfect waveguide, yes. But it's why people who make surfaces out of tin foil and things like that, where they coat things in tin foil, it doesn't work as well as doing them out of metal. It doesn't mean it won't work, because tin foil easily has that skin depth. I don't know what foil thickness is, but for it to work well, you need to start thinking about that sort of thing. In Waveguide, for things like Kumar chokes and so on, it's much less critical because that's trying to affect the beam pattern, not the conduction inside the waveguide.
Okay, so you mentioned for 10 gigahertz you had two concentric tubes, and I would imagine that would be substantially more than a couple of microns.
It is, but we do. Yeah, okay. So it propagates down it because there is electrical conductivity, good electrical conductivity between the two tubes that have been swaged together, and it can overcome these things. It's just you do get reflections at that boundary. It's a discontinuity and therefore an impedance mismatch. They're usually quite small, but this is why waveguide is usually highly polished. I mean, like all these things, the cantenna that Andrew held up it's basically made out of ribbed coffee can, but it still works. It just won't work as well as a very smooth linear surface.
Okay, that makes sense. Thank you very much.
Is there anybody else?
Are we done?
It looks like it. Well, thank you very much, Heather. That was quite brilliant. Or was there somebody else?
Yeah, Heather, if you don't mind, I wanted to show a little diagram here that might explain a little bit of the reason for the need of the so-called Kumar choke and so forth. So let me see if I can share this. Again, it's kind of difficult to get this to work. So let's see.
Top right, there's a button share that's next door to the leave button.
Right.
And
so
one of the easiest ways, if you're happy to do so, is just share your whole screen, and then that tends to work easier.
Okay. I don't suppose that's working, right?
Yes, it is. I can see it. It's propagation, infinite barrier, propagation, infinite barrier.
Okay. Yeah. All right. So that's kind of indicates the reason for the. So if you were to think of the that diagram where it says infinite barrier, if that were the edge of your cantenna, okay, you're looking at it kind of sideways, all right, and you're just seeing one edge of the aperture, and so obviously the vertical lines are the so-called the electromagnetic wave or the signal that you're trying to receive. So in a non-real universe, which is what the top diagram is showing, a signal from the side. So you're actually looking at signal coming sideways into your cantenna. Okay, and so you have a signal,
Yep.
and then the edge of that barrier of your cantenna, the outer rim of it, should theoretically block it. You would think, if it was just normal sort of non sort of electromagnetic propagation type theory. And so the bottom diagram shows what really happens is that you get this knife edge diffraction effect. So essentially the signal that's coming sideways, you think, well, it's not coming in through the opening, which is the sort of vertical direction there of the diagrams. So you would think that horizontal signal would just be blocked and it would never enter the cantenna. But as you can see there, because of this knife edge diffraction phenomena, the wave actually bends around the edge of the cantenna and actually begins to enter into the inside of it. So I don't know if my pointer is working, but basically the direction of the signal would be essentially from the top to the bottom of those diagrams. And again, a signal from the side now is beginning to enter into the cantenna. And then, as Heather was showing in those early pattern diagrams, those polar diagrams, you can see why she was getting the essentially the signal coming in from outside of the edge of the dish, and so that's basically the signal you need to try to avoid. So the reason that you have those Kumar chokes is that they sit kind of on the outside of that barrier and sort of prevent this diffraction from coming into the cantenna. So that's basically the effect of the Kumar choke. It's it's affecting the diffraction outside of the edge of the entrance to your cantenna to prevent this signal from coming into it. So I don't know if that helps. I just thought maybe I would show that and see if that would maybe explain some of the effects that Heather was pointing out. So,
another feature of the Kumar choke is that if you consider a signal going down into the Kumar choke, the signal will bounce or reflect off the bottom of the choke and come back out. And if the angle is right, then the signal will actually completely vanish. It will destruct at the frequency we want. So, yes, there are diffraction features going on here as well, obviously, as you just very nicely explained, Adrian. But also the Kumar choke, the choke part of Kumar choke, is that it acts as a negative reinforcement to the signals that are coming in from the side, and basically makes them cancel out so that they don't appear in transmit or receive. Reciprocity means that if it would cancel out when you were transmitting, it will also cancel out when you receive it. But it's a very good design. There are others. There's the Chaparral design, which is this sort of stepped funnel, which is quite a nice one as well. Most satellite TV feeds are stepped funnel type Chaparral feeds. They're even better, but they're also wider band, so not as useful for us, but and much harder to make, of course. Brilliant.
Okay, thank you very much indeed. That was absolutely brilliant. I certainly learned an awful lot from it. I'm sure everybody else did. So, moving on to the next bit of the meeting then, what I'd like to do now is turn over to each person to have a chance to talk about what it is they're doing or what they're thinking about at the moment, or any particular issues they would like to discuss. That'd be absolutely fine. And I'm just going to go through people a similar way to the way the SARA forum, so SARA meetings work online.
I have a question, Andrew.
Well, I'll tell you what. We'll start with yourself. Start with yourself, Michelle. You do. Turn over to yourself now.
Part of my activities around satellite tracking. I used to regularly take the NOAA satellite meteorologic data. But you may know that all the older one, old generation, 15, 18, 19, has been out of service in August last year. And I used the deep dipole to receive the signal. Now the only satellite are at 1.5 gig, so you need to have an antenna that can track the satellite. I was just wondering if some of you know about kind of satellite trackers that are accessible, I mean, not too expensive, so you can put an antenna and track satellite.
That's not something I do myself, but is there anybody else who got any comments on that?
It's not hydrogen line, huh? But it's fun to do.
There was there was some discussion about that a while back in the SARA member discussion page, and someone had some links for some essentially as what they call ASL or azimuth elevation trackers for the smallish antennas, kind of like the Discovery dish size type 1 meter-ish type grid antennas. And so I don't know if you're a member of SARA, but if you go search in there for the ASL trackers, you might find some links. They were from China. There were these Chinese manufactured that were not horribly expensive, but it's really hard to just buy tracking sort of mechanisms pre-built that are not somewhat expensive. You can try building your own, and there's different ways of doing it, and so that way you can customize it for your own dish if it's larger, say, and so there are designs online. You can look that up, but in terms of buying a pre-manufactured one, you can sort of do that for the smaller dishes, like I said, around a meter or so or smaller. Again, as I said, if you're a SARA member, just go on the online group and then just do search for the ASL trackers, and you might find those.
Okay, thank you very much.
Yeah, there's some really expensive ones out there, but I think Heather might have put a link on one there for the Yaesu ones. They're kind of steep. Depends on your funding level, whether that's within reach or not.
Thank you.
Yeah.
The 5500, Yaesu 5500 is, for those of us who do a lot of satellite tracking stuff, is kind of the default. It's pretty good if you want to do dish tracking, and also it has a controller input so that you can easily connect up your PC to. There's the beast. But that controller you can connect it up to an interface box to your PC, and then your PC can do all the tracking. So if you're wanting to go for an off-the-shelf solution that just works, I think most of the amateur radio people would say that's the simplest.
Thank you. Thank you.
I was just trying to see if I could see a price.
Yeah, it's quite expensive, I think, but
£650.
Yeah. But a lot of us have made our own, a gearbox and a stepper motor and that sort of thing for the azimuth, and then a linear actuator, a push rod for the
elevation.
Elevation works fine. I've used that sort of thing for the. Actually, we got that sort of thing on our 2.4 meter dish because it's a bit heavy to lift with a rotator like the Yaesu one.
So, I mean, there is on AliExpress that I've found. I've no idea how good it is. It says antenna rotator, Ant Runner Pro satellite tracking system, 360-degree azimuth and 180-degree elevation, £417. But again, plus £58 postage. So honestly, it's not that far off the Yaesu by the time you get it here in the UK. There may even be 20% to add on that for tax as well.
Okay, I'll look at it. Thank you.
The other one might be of interest. I'll put a link in. The Satnogs people, I don't know if you've heard of those. They do a lot of satellite networking stuff. They're really quite big in this game. They've got a 3D printable one, which I think that's the link I just put in.
Okay, yes, I see.
It's quite complex, but you could do that for very little money.
I guess the other
Looks
option.
interesting.
Sorry, I guess the other option is to buy yourself a used Skywatcher EQ6.
Yeah,
And
that could do the job also.
be a bit more flexible. You could use it with more sort of bulk standard astronomy software. I don't know. I don't do it myself, so I don't know what would be the best option.
It's quite a challenge to map from RA index to Azanel.
Yeah.
Most people do it the other way, but if you, you'd probably have to write some software of your own. But yeah, that's another way of doing it.
Sure. It's in terms of accessing SARA mailing list posts, that they're all openly accessible. You don't need to be a member of SARA. You do to post on there, but you can actually access them online without any problems.
I am a member. I renew my membership, so I'm a member.
For the sake of 20 quid.
Okay, thank you very much.
Okay, wonderful. Is there anything else you'd like to talk about, Michelle, regarding perhaps your own projects on Hydrogen Line?
Not in fact, right now I have some construction work in my house, so I had to dismantle my antenna. So I plan to restore my radioactivity pretty soon. But for the time being, I'm being a bit of this. But maybe if you are interested, I have another project ongoing. I just built a spectrometer.
Right.
3D printing, a very nice project. You can see with the camera, etc. I saw some people are doing also optical astronomy. Yeah. There is a very nice project called Solex. You can go on the internet. The guy is a French guy, very well known in France. He was one of the pioneers in amateur spectroscopy in France. And he has a page in English. And the project is very interesting because you can make star spectroscopy, sun spectroscopy, and the package, if you have a printer, or in fact the optical element, you can buy them from a French company called Cheliac Instruments. And so for about €400, you can have all the set of optical components to build your own spectrometer. So if some people are interested, just I wanted you to know. The project is called Solex, S-O-L-E-X. You can find him with Google.
Yeah, Christian Bjoll.
Yes.
Yeah, it's an excellent project. Yeah, I can recommend it.
Yeah, and you have done it, Andrew? Did you start something?
Yes, I have. Yeah.
Ah, very good.
Okay.
You have started to make some spectrum.
Yeah, I haven't got too far with that yet, but I've made up the Solex, so I'm hoping as spring comes on, I can have a really good go at it now.
Okay.
Yeah. So maybe you and I can speak outside of this meeting and have a chat about it. It'd be great.
Of course.
Yeah.
Okay.
Okay. Well, thank you very much.
Quite interesting.
Sorry.
I was also doing some. This is Andrew Strong. I also do optical astronomy, so I got this. I have a handheld spectroscope, which you can get from a firm in England, which shows all the Fraunhofer lines of the sun. Just looking at it, and also then for stars, you can buy these little spectroscopes, which you can stick on your telescope, and then you get the spectra of the stars. So I've done that recently.
Oh, wonderful!
And I also, by the way, talking about that, I also do the solar stuff with H alpha. So I've got an H alpha telescope, and it's just amazing. You see all the prominences. It's mind-blowing, and you can also do astronomy during the day then.
Yeah, I have the plan to do it because this can be converted to make just sun.
Yes, right.
You just take this out and you change the inside the how you call it, réseau, in French. And you can do sun scan.
Okay. Let's try that as well.
Yeah, brilliant. So, Andrew Strong, is there anything else that you would like to talk about with regards to Hydrogen Line today?
Yeah, well, I can tell you that that's as far as I've got still, right? And I bought the RTL SDR
Right. Okay.
dongles. They're all there, just waiting for me to do something with them. And I probably better have another session with you. I think I've got everything now, including a special laptop to install Ezra and so.
Okay.
And
Yeah.
that's as far as I've got.
Okay. Well, we'll set one up, and I think we said last time if Ted's available, it might be good to have him join us as well, because I think there were a couple of particular issues you were having where it might be helpful to have his expertise. So we'll see if he's available.
And also listening to all Heather's talk. I mean, I did do physics at university, and so in principle, I know all about Maxwell's equations and everything. And I must get back to actually to learning how to actually solve them on a computer, which we never did at university. You learn how to do analytical solutions. And I've learned from you that this is the CST thing. You can actually do it. I might try that as well.
Oh, I think you're taking on a big challenge myself. Heather goes on how good it is, but I think, gosh, that'd be very impressive indeed. Yeah. Okay, who have we got next? Dave B. Would you like to chat about anything?
Yeah, hi Andrew. Yeah, okay. So what have I done over the last period? Well, I finally completed a project I've had running for a while to extend my antenna from 1.5 to 1.9 meters in diameter.
Oh, wonderful!
So I've completed that, but I've yet to test it. So
so how did you extend that, Dave?
So, well, I've done it in a modular form, Andy, because my 1.5, I can manage it. I can pick it up, carry it, just about deal with it. And when you start going beyond that, things start to become quite unwieldy. So what I've done, I've made some rings that go around the outside of it. I haven't got any photos at the moment, but I'll maybe do something another time. So which bolt on and extend the diameter up to 1.9. So I can set it up as 1.5 and then put these bolt-on extensions on to get to 1.9. Yeah, so it's sitting there in the garage at the moment waiting to be tried, and I'm hoping to have a go later on this week.
So what did you make those bolt-on extensions out of?
Oh, aluminium angle strip and mesh.
All right.
So it should continue the parabolic shape out.
Right.
In the same way.
Oh wow.
So it took me absolutely ages. Didn't plan, I didn't think it would take me anything like the time it took, but yeah, I've got there anyway. In the end, anyway. So done that. Meanwhile, I've got quite interested in looking at, and I know you've been interested in this, Andy. Integrated multi-day Ezra. Looking at several days at a time in Ezra. And Ted's given me a huge amount of help with this to do RA and velocity plots in an integrated form over multi-days. And again, I've just started to get some quite interesting results from that. After using the modules that Ted's made for me and taking on board the tips that Ted's given me. So again, early days, but just starting to get some results on that. And so both of those I'm hoping to go together into a project to compare performance of, let's say, single multi-day Ezra integrated results. Look at the performance. How does performance improve when you go from single to multi-days? And I'm looking at that. I want to also compare my 1.5 and 1.9, see how that compares. And I might also extend that to look at 8-bit and 10-bit in Ezra as well, and again do comparisons. So looking at the same spot of the sky, so I can look at apples for apples, and just to see, what difference, if any, can I see. So yeah, early days. I've saved all my time up on the 1.9, but meanwhile, Ted's got me going on the RA velocity plots, and so the next few days should be quite interesting.
Wow.
The weather holds.
So maybe at the next meeting you'll be able to present some results from those things, possibly.
I hope so. I won't promise anything, but yeah, maybe.
Oh, okay. No problems.
I'll be in touch. I'll let you know.
No, nobody should feel obliged or stressed to try and produce.
I know. I don't feel obliged. I'm sure I'd like to. It's just a question of will I get there or not. Keep you informed of what progress I get, if any.
The reason periodically people keep asking me to make modifications to my ex-military array and say, oh, maybe if your coax was shorter it would work better, or if you did that with it or did this with it, but I refuse point blank to change that at all, because being an ex-military thing, it may not perform better than another antenna, but it always works, and I'm not going to change it. And so when everything else is falling apart around me, I can at least turn to that one and know it's still producing data. So it makes me feel good.
I can believe it.
Anyway, okay. Well, thank you very much, Dave. That's brilliant. So how about the other Dave? We got David W. here. David, anything you want to talk about?
I don't. I just want to say I'm a complete beginner. This has been absolutely fascinating. What a great group of people. And I would like to re-engage. This is great.
Well, you're very welcome. I mean, this group is as much designed for beginners as it is for people who are a bit more experienced, and I appreciate after that staggering talk by Heather, which was quite brilliant, but it was also at quite a high level, and I could quite easily understand if you felt, gosh, if this is what this group is about, then it's not for me. But I want to emphasize that please talk to us about the things that you're doing, even if it is really you haven't got started, you don't know how to get started, because we've all been there and we all got help from other people, mostly on this group. And we're very happy to offer help to other people. So
that's great. Thank you very much. And Heather, that was a really interesting talk. So thank you.
Well, that's brilliant that you found it useful. So have you got any thoughts at the moment about any project that you'd like to do yourself? It's certainly not required to be a member of this group, but is there anything that you're keen to have a go at, or at the moment are you just still just watching and getting a feel for the subject?
Yeah. Pretty much just getting a feel. I've acquired a couple of antennae and just working my way through getting the software loaded up. So I'm hoping over the summer to do some interesting stuff.
All right. What software is that you're loading up at the moment?
That's a very good question.
All right. Okay. Fair enough. I won't push you any further. It's again, I know exactly how you feel. I had an interesting experience. We started this hydrogen line where I got it was SDR sharp, but it was producing a signal. And I thought, well, that frequency's wrong. There's obviously something majorly wrong with my with my setup, and it wasn't until several months later that I realised I was just seeing the Doppler shift, and there was nothing wrong with it at all. But the problem is when you don't know, do you? We're all sort of located usually a long distance from anybody else that's doing this same type of stuff, so it can be really frustrating. But I meant it when I said very happy to offer any help, and if you want a Teams meeting or a Zoom meeting at some point to discuss anything, you're very welcome to do so. I'm very happy to offer that. Other people have done that for me, and I'm very happy to give that help back if I possibly can. Just let me know.
Well, thank you. No, that's very much appreciated.
Okay. How about Ted here? Ted, is there anything you'd like to talk about?
Well, I'm still getting things together. I've bought quite a few components that I'm going to need, like a SMA kit and things of that sort. So, a couple of questions. So I bought the Noelec SDR, and
which one have you bought?
It's a Smart E.
As long as it's got the T on the end, you're doing well.
Yeah, it's the Smart E.
Yeah, I say that to anybody
I find
here.
it-
If you're thinking of buying any of the SDRs, please make sure you buy one that provides a bias T. I know you can get away without one, without a bias T, but it makes life so much easier. It'll give you options in the future. If you don't know
Okay,
what a
good.
bias T is, again, feel happy to send me an email and ask me. There's no such thing as an idiot question.
We all start off as absolute beginners, I think, Andy. So there's a steep learning curve at the beginning.
Yeah.
Anyway, software-wise, I haven't made full use of the NoElect website yet. It's a bit hard to follow. And I found the first thing that my Raspberry Pi found, which was, what was it? Cubic SDR or something like that. And anyway, I managed to get Radio 4 and Radio 3 on it, on FM. So I thought, well, this is a good start. I found the NoElect SDR runs very hot. So I've invested in some heat sinks, which I'm going to try and strap onto it to keep it a bit cooler. I mean, it's like 50 or 60 degrees, I should think. And that's after 20 minutes.
Do you know, I bought one of those SDRs, and I was trying it out on a test system the other day, and I was a bit shocked how hot it got as well.
I've got a can.
Oh, well done.
Farrow and Ball. It's 15.5 centimetres diameter, so I think that should do okay for hydrogen line. I need to extend it, preferably anyway. So I was wondering what to do, and I thought, now somebody I met at the BAA meeting suggested he was thinking of using chicken wire. Well, I've had nothing but bad experience with chicken wire. Chicken wire goes where it wants to, not where I want it to go. So instead I bought some 6mm square mesh. And like this. And it comes in a pack of 10 600 by 900mm sheets.
Oh, very nice.
I thought, what can I do with those? Actually, it'd be good for extending a satellite dish, I think. And as
I was thinking that.
yeah, it wouldn't add much to the weight, and it won't resist the wind too much. So I think it might be quite good for that.
You should get Dave Bracey there to. I should have a chat with him. He'd tell you how to use that.
He said he was using mesh. He didn't say what sort of mesh. Anyway, I thought, well, maybe I can just, if I'm going to extend it, why don't I make a horn antenna? And I thought, well, if I'm going to do this, I might as well do it properly and go for an exponential horn. So I found some old MDF and I've sort of cut a template so I can model it to that. But next time you see me, my hands are going to be in shreds, I think, trying to mangle this mesh into a horn shape.
So the day out later in the year is to go and see Ted Parton's 4.5 metre hydrogen line horn in his backyard.
It won't be like, I think it'll be about 500 millimetres wide, that's all. It's
So what type of mesh did you use, Dave, on your extension? Was it this same sort of, what did you say, 6mm?
Oh, yeah, I bought mine from eBay. So it's, let's see, I bought it's 3 metre rolls, 0.5 metre wide, and you can, for about 15 quid, I think, and you can buy it in what's called small, medium or large mesh. The large mesh was, this is talking about the apertures, was 19 by 9, I think, from memory. But I've actually gone for the medium, which is, I think it's 6 by 4 diamond, open diamonds in the middle. Which you know, I'm sure both would be fine. I found that the smaller mesh was more robust, a little bit easier to hold a shape. So I've gone. That's what I've gone for. But I formed mine onto some. How can I describe them? some sort of frames that hold the parabolic shape, and
Right.
they're a radial pattern. I'll put some pictures up somewhere. I don't have it, unfortunately, at the moment. But yeah, you know, mesh is good. But yeah, I do fold the edges over. Ted, I do fold the edges of mine over, so you get a
For
rolled
safety.
edge, because it's deadly.
Yeah.
And I've got the scars on my hands. I'm looking at right now. Still see them. So yeah.
Actually, on a dish, you could walk into it by mistake, couldn't you?
Yeah, very much so. Yeah, especially when it's at eye level. I'm very careful about that.
Yeah.
Ooh, sounds dangerous. So we should ask Heather, Andrew Stowski here and Adrian as our resident experts on all things aerials. What size mesh is ideal for the hydrogen line, and you know, what's the limit to what sort of size you can use? Say if you're extending a satellite dish, or even just making a whole antenna out of mesh.
The rule of thumb of a tenth of a wavelength is kind of a good minimum.
It's about 2 centimeters, or 20 millimeters, or if you're American, about 3/4 of an inch.
The smaller the better, but yeah, that's kind of the limit. The 1/10 wavelength.
All right.
We spent 2 years with chicken wire and we couldn't get any signals, and then eventually we changed it to aluminium mesh and we got signals. So stay away from chicken wire. The other thing is that the smaller the hole, the larger your wind loading.
That's a good point.
That's true, but I have been pleasantly surprised about wind loading on mine. Even at the 6x4 hole mesh, it does seem remarkably, on a 1.5 metre anyway, it does seem remarkably unaffected by wind. We've had quite a lot of wind recently, haven't we? And I've been pleasantly surprised how good it is. I'm a little bit worried, I must admit, going up to 1.9, that I might be end up with it all wrapped round the garden, but we'll see. But yeah,
We're up at
good.
we're up at 4 meters with similar size mesh.
Okay, yeah. So,
Dave, I have a question for you. For supporting your mesh, you have support that are parabolic shape. Did you make it 3D print support for the mesh?
No, I've made my frames. From aluminium angle and strip.
Okay. And they are straight?
No, they're curved to form a parabolic shape. I did for the 1.5. It uses the I forgot the guy's name now. The Japanese chap. It's a geodesic dish. So it naturally forms a shape that's not exactly parabolic, but quite, pretty close to it.
And for the extension, you made yourself?
Yeah, I've made these bolt-on extensions again that are all, imagine a lot of radial spokes, but they're in approximate to a parabolic shape. That bolt on to extend the parabola, or my approximation to a parabola. Again, I have to say, not tested yet, so it might be hopeless, but time will tell.
Two comments. If you remember, the beam pattern of your feed is critical to the size of the dish. If you've got a much bigger dish, if you've got a feed that works well on a dish, and then you extend the dish, it may not do anything because the feed may have pretty much petered out by that time. The other thing is that one of the main reasons that amateur radio people put extensions on dishes is, well, there's two reasons. One, it improves the side lobe reflection of the dish. And the other one is it prevents radiation from behind the dish from getting through to the sensor. So these are two things to consider. If you've got if you're just doing hydrogen line, then you're not too worried about it because you're going to be filtering very heavily very early on anyway. But if you're doing wider band things, then getting rid of the thermal noise from behind the dish when you're pointing it at the sky is a useful thing. So, yeah. So worry about the beam pattern of your feed. It may be that you make a bigger dish, you want to make a better feed or a different feed.
That's good info here. My F to D has dropped from 0.37 to about 0.3 in doing this. So yeah, don't know how bad that is. We'll see.
But it depends on what your feed F over D design is. If it matches well.
Okay.
For amateur radio point of view, we normally say that you should have a bit of overspill on transmit and a bit under for receive, so that you can get rid of all these edge effects that where it was Adrian mentioned earlier. But yeah, matching things together is quite useful to get good stuff out of bigger dishes.
Okay, thank you.
I know that Alex Pettit on the SARA forum often states in his view that the most useful thing of extending a dish is to get rid of ground noise. And as such, he doesn't care too much whether you're following the parabolic curve or not. Quite happy with flat extensions. Just simply to try and stop stuff from bouncing off the ground, the trees, the house, the wherever that's around.
So this is more important than this extension.
No, he thinks that extending the dish is very useful in his view. He's sort of the SARA resident antenna expert with Adrian here, really. But his view is that ground noise reflections, or by which he means not just ground, but particularly trees and other things around, it creates one of the major sources of avoidable noise in a radio telescope system. That's what he believes anyway, and his measurements for tests that he's done seem to back that up. So extending the dish and maybe putting one of these Kuma chokes on would be, in his view, one of the most useful things you can do.
Okay. Well, as I say, I've got my plan to do these apples for apples tests. So I hope to be able to definitively say if my time has been wasted or not.
No, I'm very much looking forward to your results. I'm very much looking forward to those results. And after all, as a hobby, this is what we do. This is why I try out different things. It's nice for Heather to say, oh, well, maybe Andrew can avoid doing all these tests, but actually I'm doing it for my fun as much as anything else. So, I've got working hydrogen telescopes. I've successfully mapped the Milky Way. I've successfully demonstrated the sort of smoking gun for dark matter. You might say, what else do I need to do? Well, I want to get that bigger fish. I want to just try it in a different way, use a different rod, you know. We'll have to see. Anyway, that's brilliant. I think this discussion's fantastic. Thank you. So we've got left here. We've got, I think we're left with Tom here. Would you like to say, is Tom still with us? Would you like to say anything, Tom?
I think he's left.
Has he? Oh, okay, I'm just trying to pick up on who's left. Yeah, I think you're right.
No, he hasn't. I don't know. People are marked as left, but
I can't see him on the list anymore. No, I think he's gone. Okay, so we've got Tom. Tom gone. Okay. And Francesco, would you like to talk about anything? Or ask any questions, or comment on anything that you're doing, or just generally chit-chat? Francisco? Still down as being with us, but on mute. Perhaps nothing to say. Okay, or maybe sometimes people don't have the capacity to say anything very much. So, according to my calculations, we're left with Ted, Adrian, and myself. Is there anybody else that we've missed out on? No. Okay, Ted, Anything you'd like to talk about, my friend?
Nothing comes to mind. It's just fun to listen to all these presentations. Thank you, Heather. That was great fun. But Andy, I have a question for you.
Oh.
You got this military antenna. Maybe you call it ex-military antenna. Have you ever seen another one? Is yours the only one in the world? How do I get one? You know, that kind of thing.
I've looked. I've looked because I had this idea I was going to do interferometry with two of them at one point, and I cannot find any others anywhere. There must have been some others, but I don't know where you'd find one, and it's very difficult to find any information about it. I eventually found a diagram on one of the ptarmigan triffid advertising literature for the military when it first came out, which just happens to show a bit of a battlefield environment and some sort of vans around, and one of them's got what is clearly one of these antenna on the top of it, but it may well have not been a very good antenna for all I know.
So, so I continue with, so all the other ones were lost in battle, I guess. Okay. Or yours is a national treasure, or a deep secret that is hidden, obviously, you know, a conspiracy. When it came out, you say, any idea what year that was?
Oh dear, this is going to make myself embarrassing when I get it completely wrong. I have a feeling it's in the 1970s, but I may be totally wrong.
Yeah, it was designed in the 70s, certainly.
Oh, there we are. Thanks, Ted.
Okay.
That makes me feel better. I thought really putting my foot in it, I thought for a second. I think it was 1970s.
It was Plessy designed.
And you're using it for 1420 megahertz. Any idea what it was really made for? Is there any label?
No label. It's got that to.
It's part of that secret again. Okay, good.
I did measure the dipoles at one point, because you can see the 16 dipoles on the front of it, and they did seem to come about right for 1420, but exactly this sort of a military band, which I can't remember what the military band is, but it sort of covers the 1420 wavelength. So it was designed for a particular transmission and a particular band. And it was a battlefield system.
Well,
and it's
one of the
sticking up
bands is
here we are.
one of the bands is 1.35 to 1.85 gigahertz.
There you are. Then
Perfect.
that's what it was designed for. Somewhere in there.
Okay, cool. Well, it works great. Thanks. Take care of your national treasure.
I got to point out. I got to point out to everybody. I have tested it, and it is no better than a 1 meter dish. It's about the same. So it doesn't perform at a higher level. It just has, like all military kit, the advantage of being extremely robust. And you can throw.
Well, you're just not allowed to tell us how good it is. Okay.
Well, it has one other major advantage. When I started off this whole business of radio astronomy, my wife was not keen for me to have a dish. She's only lost that one now because I got one, but which I sneaked in at some point. But at the beginning, she didn't want me to have a dish, so she felt that ptarmigan array looked like a barbecue on its wooden mount, and that was okay. That could go on the patio on this on its barbecue-like look. So I mean, these are things which are really important. Whether the powers that be in the household are happy with what comes in there. I mean, not everybody's got a wife like Heather who doesn't mind radio kit hanging around. She is an enlightened individual.
I don't think I have any choice in the matter, to be honest.
Oh, I still think you're enlightened. I think you're enlightened. But there we are. Okay. Well, thanks very much, Ted. Thank you. So it's good. Adrian, my friend. How about yourself?
Yes. Actually, I have maybe a little addition. Again, back to the very excellent presentation that Heather gave us today. But she was referring to and trying to attempt to measure the beam width of an antenna. And so she held up her dipole that you would put on the signal generator, and then you would kind of scan that across your antenna, that your dish antenna that you want to kind of measure the beam width of it. And so what I have here is a different version of the antenna that Heather demonstrated. So she was showing a dipole, and so dipole would work just fine if you can find one for the right frequency.
Sorry, Adrian, are you
dipoles
sure that's not an Imperial cruiser?
Yeah, well, it kind of looks like one, doesn't it? Yeah, it's either that or sixth generation fighter jet, one of the two. But anyway,
Oh yeah.
I don't know if you can see here these lines coming across it.
You
So
can't
these
see
are
you,
various-
Heather, because his Imperial cruiser's in the way of his eyes, so he couldn't see what you held up.
So I'm not sure if that's showing up, but so you have these lines here, which are essentially kind of like dipoles.
Adrian,
Not exactly.
Heather's holding up a Christmas tree for you.
Oh, I see. Okay, fine. So she's got one also. So again, advantage of one of those. Hers is smaller though. So Heather, will that one do? Will that one do 1420? That looks a lot smaller. It looks for a higher frequency.
It's certainly microwaves. I don't know whether it quite goes down
Yeah.
that far, but it might do.
Okay, so see that's the advantage of these type of antennas, and what they're called log periodic antennas, or for short people call them loggies. And so the dimensions of these vertical stripes, which are kind of like they're kind of like dipoles, but they're not necessarily dipoles, but they're sort of progressively of different lengths. And so what that does is that provides a means of using the same antenna for a wide range of frequencies. So if anybody's familiar with log periodic antennas, that's what this guy is. And so it's got I'm not sure if you can see it, there's an SMA connector here. So this is where you connect it to your receiver or your transmitter. And so like this one here, for example, is able to be used from 800 megahertz to 6 gigahertz. So that's a huge bandwidth. And so as a sort of alternative, if you can't find a dipole that's good for 1420 or at least thereabouts, even like Andrew said, his military antenna, those dipoles are for a range of frequencies. But if you can't find a dipole that's more or less for the 1420 frequency that you want to use a signal generator to output a test signal and measure around your dish, then one of these log periodic antennas are pretty cheap. You can get them on eBay, and they'll cover the range of 1420 and almost anything else you can imagine. And so that's kind of what I wanted to point out, that this is another option if you want to attempt to do your beam width measurement for a dish. And so you would just you would be able to use one of these guys for that particular frequency range. And they sell them for different sizes, for different there's bigger. I have another one that goes all the way down to 400 megahertz, and then they have smaller ones for higher frequencies, like Heather was showing for maybe 10 gigahertz or even higher. And so they're useful for that application. Anyway, I just thought I'd point that out in case. I'm kind of interested in doing that myself, actually measuring the beam width of some dishes that I'll be putting up, and have a signal generator that'll do a 1420 signal, and just kind of crank it down so it won't disrupt all the radio astronomy that goes on here, and where I'm located, which is kind of ridiculous because the RFI at around 1420 is pretty horrendous. I live pretty close to a military base, and it's just they use every single wavelength in the spectrum seems to be contaminated by stuff that they generate. So anyway, just as an example of a logging that you might want to look at for the signal transmitter.
Oh, that's excellent.
Just,
Yeah, carry on.
I'll just add to that. here's an alternative. It's a little tripod with a dipole, but it's these extendy things. So this antenna can start off at whatever that is, or you can plug in a bigger one, and yeah. So that again, it's only one frequency at a time, but you can set that up.
Okay, brilliant. Okay. Anything else, Adrian, that you'd like to talk about?
No, that's pretty much what I have for today.
Okay. Well, I got a couple of things very briefly to show. What was it I want to show? I forget what I've discussed where these days. So I may have discussed this last time, but just to show it again because I brought it up. You might remember I was designing a tunable cantenna. So based on an aluminium tube, one tube, and it's a piece of flue pipe which is designed for sort of like wood burners, etc., in houses, and it's the inner lining to go on it. You get it cut to size, something like that, and then if you've got that size of tube coming outside, you're liable to get sort of leaves and dirt and all sorts in it, and perhaps bird droppings, etc. So you can actually buy these slip-on ends, which just literally just plug into the end. So, but the other advantage of those is you can then move it in and out, and the advantage of that is that the distance from the chassis connector, the N-type chassis connector that I've got on there, to the end of the tube can be varied if you want to. The other thing I did was, you might remember, is on the inside I've soldered a brass connector in there, which you can just about see, which is one of these sort of two-sided connector things that you have between circuit boards. And then I've got a small piece of copper threaded rod which goes into it, and using a nano VNA, I turned the rod until I got it into where it performed best on the nano VNA, put a little dab of super glue on that. So according to the nano VNA, that's now performing at its optimum, and I now have just to try it on a telescope and see whether that actually is the truth or not, and possibly with my Kuma choke that I'll be making there once I've got it so it's a little bit looser, so I can fit it right up. So that's my plan. Let's give that a try. But I've also got my other feed to try. It's another hydrogen line feed, not made by myself, I would say, but I've got to try that one on something as yet and see how well that works. So that's that bit of it. And the next thing I'm going to try, Ted doesn't know this, so I hope he doesn't get annoyed with me for trying it. I have to emphasise that what I'm going to show you now, something we showed or Ted demonstrated at the GNU radio meeting on Saturday, and for his sake, I've got to say that this is very much a beta in development bit which he doesn't support. So I don't want just people aware of that. But I just think it's quite exciting. I'll just give you some inspiration. So we have a separate GNU radio group, but sometimes we look at that with Hydrogen Line, which is where it's relevant. And where have we got? What did I put it on? Here we are. So this is a version of EasyCull that Ted has developed, but this time it's under GNU Radio and produces EasyCull data files. And I've added a few extra knobs and things on the front of it just to make it slightly more user friendly to things like your latitude and your longitude and all that sort of stuff. But you can see it there with a clear hydrogen spike, and that's actually a live recording going on at the moment, using offset frequency at 1423 megahertz for its reference frequency.
So I encourage its use, but I don't support it, meaning I don't answer many questions about it. And what we're trying to do is simply gather data even faster. More readings is better, and I guess we're trying to support other kinds of SDR hardware, AirSpy, SDR Play, EDIS, all those kinds of good stuff.
Yeah. So I hope you didn't mind me showing that, Ted. But
no, you get to support it.
I get to support it. Just for your interest, I have since the weekend been having a look to see whether I can find some way in GNU Radio to allow you to switch between different types of receivers live as it runs. And as far as I can tell, unless somebody writes a Python script to do it, you can't.
Andrew, is it a new version of EasyCall?
Yeah, well, we have a separate GNU Radio group, which I don't know. Do you know GNU Radio?
No.
So GNU Radio is, I might better pull it up so you can see it. It's a piece of software that allows you essentially to write Python without necessarily knowing Python. In the old days, I used to have when we used to write websites in HTML, you remember those, about a century ago sort of thing. I used to have a program called Net Objects Fusion, and it was what you see is what you get, in the same way as Word revolutionized word processing, allowing you to just put on the screen what you wanted. Again, likewise, Net Objects Fusion allowed you to do that with HTML, and this is where GNU Radio, which is an open source piece of software, which hopefully you can see now, allows you to do the same thing. So basically, if I open one of our existing, this is an AM radio written in GNU Radio here, for example.
Okay.
And so you have these blocks that you can put in, and then you can choose ones if you wanted, for example, to put in some filters. You could choose a filter, maybe if we just wanted an FFT filter or just band reject filter or something, we can add it in. And then we can just add in arrows between one and the other. And if it's red like this, those red bits mean there's an error of some description that needs to be resolved. It looks really intuitive. It's perhaps not as intuitive as it looks, but it is a very powerful system, without doubt.
Okay.
And as I say,
Andy, you said you didn't get many people attending yesterday, but I wasn't aware of it yesterday.
So it was on Saturday, and that may well be the issue. I got to say, I did advertise this Hydrogen Line group a lot more than I advertised the GNU Radio group, and that may be part of the problem. So I think maybe that's a good bit of feedback, actually. Thank you for that. Okay.
You said
Yeah,
Saturday's meeting eventually will be posted as a video, Andy? Would that be on BAA or what?
Yeah, it's already there as of this morning.
Oh, there we are.
So
you can give us a link.
Yes, if you go on to, I sent it out to you separately because at the moment I'd have to go on to my my email, which would then appear on this video. But but it's easy to find. You just go onto the British Astronomical Association YouTube channel, go to YouTube, type in British Astronomical Association, and it will be the latest video that's there. Or type in Hydrogen Line, or type my name, Andrew Thornett. It will appear. Sorry, GNU Radio, not Hydrogen Line. Sorry, we're Hydrogen Line. Sorry, type in GNU Radio, GNU. There's a message came up a second ago. What was it? From Richard to say you can use a version of Scratch to produce Python code, not strictly radio astronomy, but is anybody going to track Artemis 2 by its transmissions? I don't know. Ted's already found the GNU radio meeting from Saturday and put it in the chat. Yeah, worth looking at, because Ted gave a detailed demonstration of the software that he's produced and the process of developing that, which is quite insightful, but into how you produce GNU radio code, and quite interesting in the whole process of trying to produce a viable radio astronomy piece of software.
And Andy's providing worldwide support.
I'm providing worldwide support. I'm charging for it as well. It's not very good worldwide support, I've got to point out.
Just for your reference, Andrew, the GNU radio has switches and selectors, which would allow you to have switch between different receivers if you just route the signals through a switch.
So does that mean you run all receivers at the same time on the same antenna? And so now we get into awkwardness.
No, you could switch between those, so you'd have your signal from your antenna.
Right.
I mean,
you get to pick which output you want, but
yeah, and then you have a selector or a toggle switch to say send it to this receiver or send it to this other receiver, and hopefully the graph will be optimized enough that it will only be processing whatever receiver you've selected, or vice versa if you want to do different antennas to one receiver.
I don't think we have a match here yet. They have blocks that talk to SDRs, and there's no way to get to the antenna signal before the SDR.
Is that what you were trying to do?
Andy would love to disable and enable different receivers.
Yeah, I mean, if you pulled up something like SDR Sharp, while you're running the program, you can select and say, well, I want an RTL SDR, or I want a B210, or I want an AirSpy, or whatever.
Just because at this location, that's what you would have, for example.
Yes, I mean
that would. Andy wants to send out one program that could be switchable.
Exactly. Trying to find something for people who don't know very much about the software, where they don't have to, as it were, get under the hood to change over to their software, and where we wouldn't necessarily have to produce sort of 10 versions of the software to try and accommodate people's different types of receivers. I mean, this is a problem that Ted's been having here with Easy Radio Astronomy generally, in that he produced it for RTL SDR because that was worked very well. It was very cheap to buy and readily available. But we're now finding that there are people particularly with AirSpies, and I've got an RSP Duo which I've been trying to use with it, which is an SDR play device and things like that. And so if somebody's already got an existing SDR, they might not be keen to go and buy another RTL SDR just to run with this software.
But you've also got enables for the different radio blocks, I think.
Enables?
You
are they a separate block, are they?
And so what we may do is put one of each on the program.
Oh, I see what you mean.
And then teach the user how to enable the one he wants. And only one of them is actually operating.
Well, yes, at the moment that's the best option we have.
I think you could do that programmatically, though. On your GUI, you could provide a switch for each one and then feed that switch to the enable block of the... it may not be visible on the GUI. You may have to enable it through the Python enable rather than through the GUI, but I think that would still work.
Yeah.
So you'd have all the receivers on the graph at the same time, and then add toggle switches on your GUI to feed enable signals to your different receivers.
Yeah, I think this is something to be continued on perhaps back in the GNU radio meetings, but yeah, I think that's things to think about.
Yep.
Definitely.
So I haven't been to any of them. Like others, Saturdays aren't a great day for me.
Yes, I'm going to. I think I've sent out. I'll send one out to you as well. An email to ask you which days would suit you best, because I think we as we were reviewing the day.
Right.
GNU to Heather. Talking of which, as far as this, we seem to have lost most of our group at the moment. But as far as people are concerned who are still here, which days of the week suit you best for these particular meetings for this hydrogen line? Is Monday still the best day, or are there other days that would be better?
Monday's great for me.
Okay.
So,
Yeah, it's good for me.
yeah.
Good for me too.
Yeah. Okay, we'll stick with Mondays. So so let's have a look at the next date, or the date for the next meeting. It's on my diary app. So normally we do it on the first Monday of the month, which would be, if we did that, the 2nd of March. I just have to check because we're going off to 18th of March. We're flying off to the Far East. So would 2nd of March still suit you all?
Okay.
Yeah.
Okay, 2nd of March. Next meeting. Oh, one thing I did forget to do was apologies, Paul. Paul Hearn, who couldn't make it tonight, wanted me to give a little bit of feedback of where he was. Just reminded me, looking at my phone. So Paul has said, sorry we're away, so we can't join this meeting. My progress: I've constructed a feed horn. I've got an inclinometer breadboard that's working. PCB layout is done. Motor drive schematic is done. And my next jobs are to integrate my low noise amplifier to the feed horn, test my motor drive, fit my dish to my stand, and install Ezra on a PC or Raspberry Pi, and watch all of Ted's excellent videos again. And he wanted to say that Dave Bracey...
It sounds like, for me,
Yep.
the easiest option might be for me to buy the RTL SDR rather than try and make the new elect work with various softwares and go straight into Ezra.
Well, the new Elec is an RTL SDR version.
Oh, is it?
Oh, well, it's an E4000 chip, which is slightly different from the RTL SDR, but honestly, they work with the same drivers. There is a slight window of it's about 1,100 megahertz, I think, where you don't get any reception for a small window, but it doesn't affect us, and it does go up to a higher frequency, up to about, I think, 1.7 gigahertz. But again, that doesn't bother us either. So yeah. So it's the Nest DRT you've got, isn't it? Or something like that. Anyway, so yeah, that should work with exactly the same drivers. Don't worry about the temperature on it.
Okay.
Just run it hot for a while, and then eventually you might want to stick it on a heatsink. But bear in mind, the biggest advantage of the heatsink is to try and stabilise the temperature rather than necessarily cooling it.
Yeah.
If you're going to cool something, that would be the Sawbird H1. But yeah, that's it. That's what I've got. Smart T, the Nest DR Smart T. Yeah. So yeah, it does run hot. I practiced it myself, and I've also gone and bought a heatsink off eBay, a second-hand heatsink to give a go at that. But at the moment, to get it working, I wouldn't worry too much about it.
So if I go for SDR sharp, and then I can get Ezra, is that right? Good way to go?
Yeah, whichever you prefer. Sorry, Michelle, what's it you were going to say?
I say I've worked hours and hours. It's getting very hot, and doesn't matter, it works.
Yeah.
No problem with it.
With some potential advantage. If it runs hot, it might be more stable. if it's hotter than the surrounding environment. Or am I talking rubbish, Heather? What do you reckon?
I'm sorry, I wasn't paying enough attention at that point. Ask me again.
She's going to sleep. She's going to sleep.
I watched the Sarah talk from what's it called, Cook's Lounge from Australia,
Yeah.
and you can imagine the temperatures they get. So actually, when the temperature gets over 40 degrees, their receiver overheats and they lose signal to noise.
How hot does your kit get, Ted, up there in Colorado?
I suppose it gets hot, but we live here, so I don't know. They're supposed to run hot. I mean, that's kind of the way they're designed. Indeed, the heatsink is just to stabilize the temperature so that it moves, the temperature changes more slowly instead of dramatically. I haven't worried about the heat on these guys. I agree they get hot. Okay.
Yeah, the Australians were thinking of investing in Peltier coolers.
Yeah.
That's a method to stabilize the temperature.
Yeah, that's right.
It's a lot of effort.
I have used it on my roof, exposed to the sun in summer, where it got very hot. In Paris, like in London, it was 35, 38, and I didn't have problems.
Okay.
Yeah. I mean, bear in mind something like a Daystar solar filter runs the Etalon at 100 degrees centigrade, and that's also to stabilize the temperature, which is required for the narrowband. So it isn't necessarily a problem that something is hot.
Yeah.
Well, there is one consequence which might have a little bit of a influence on it running so hot, in that these all the SDR receivers essentially have a particular clock that runs in the receiver, and the clock is set by pretty much a crystal, a quartz crystal. And quartz crystals have this particular sort of aging that occurs as they're used, and heating accelerates that aging. And generally, what aging does is it shifts the frequency of the crystal. So whatever it was manufactured at, it drifts out of that frequency. So the net result will be that. But I think most software nowadays, you can essentially calibrate the frequency you're receiving. But with the RTL SDR, after extended use, you might see that it has drifted off frequency, and you might have to calibrate your receive software for the SDR in order to compensate for the crystal change. I mean, there's specific crystals that are that even sit what Ted was saying, maybe instability, in that they sit in an oven, and they're oven-controlled crystal oscillators, and the oven, what the oven does is it heats it to a particular temperature, so the crystal always sees that temperature.
Yeah.
Because if you have a circuit that starts out at room temperature and then heats up significantly, that crystal frequency is going to change. So once it's stabilized at a particular temperature, that the frequency of the crystal will stabilize at some point. But in between, it will drift as it heats, unless you have one of these oven-controlled crystal oscillators that's running the system. And there's some other versions also that compensate for the temperature. It has a sensor that senses the temperature, and there's almost like little software in the crystal that sort of adjusts for the change in temperature. But anyway, so that might be one consequence. And then the other one is just that integrated circuits do tend to if they overheat, they can burn out. So that's another possibility. Lifetime for the SDR might be shortened if it runs excessively hot.
Yeah, but I mean that's the advantage of these cheaper devices, isn't it? That sometimes it's just easier to be prepared to allow things to die and change them to a different one, rather than
Yeah, maybe that's right.
if you have a £500 device, you're much more concerned.
Yeah, well, the more expensive devices don't usually run as hot. They have other integrated circuits in them that run a little bit cooler. So that might be one advantage. I wanted to kind of just briefly change the subject a little bit and address. I know that Richard put on a kind of a question, I guess, on the chat, and I actually have a question for him. Too bad he's not able, perhaps, to come on and describe. But he mentioned Scratch, and I've sort of heard of it. It's kind of the block sort of software that you can use in some aspects as more of a teaching code. I'm not aware of it being able to generate Python, but that's kind of an interesting point. And then the other one, he asked, is anybody thinking of even trying to perhaps monitor the Artemis moon mission? And so I wanted to, I'm sort of thinking about doing that, but I've got so many other projects and things I might not probably be able to get around to it. But I have this, I don't know if you can see this. This is an LNA for the right frequency. Now the Artemis transmissions will be on approximately 2.4 gigahertz. And so you need a particular feed for that frequency, around 2 gigahertz. And so they sell these things that used to be for like these sort of television networks that were around at one time. And they have these for various different frequencies. You can get these from the Chinese suppliers, the AliExpress and whatnot. And they're for a few different frequencies. This one specifically will be able to pick up from about 2.2 to about 2.5 or 6. So it'll be in that 2.4 range. And I think the transmissions of Artemis will sort of be in that range. So basically the way it's kind of, there's another plate that goes on the end here, kind of like a little a reflector. And so it actually goes, you'd think this would be pointing towards the dish, but in fact the way this mounts is it's away from the dish, and then this is at the focal point. So the dish would be back here behind it. And there's a little coax connector there that basically is where you feed in the voltage and the signal, pretty much like a standard TV LMB sort of system. So I was thinking of maybe putting this in front of a 1.8 meter dish, and which I would have to assemble, and see if I could maybe get at least a carrier from Artemis. I don't know if you're all familiar. Ted is a member, so he can maybe describe more about it. There's another group that's called DSES, which is out of Colorado, and it's called the Deep Space Exploration Society. And they do everything from radio astronomy to trying to monitor some of these space probes, like the Voyager, for example. And they've even attempted a project which is to bounce a amateur radio signal off of Venus. They tried this last year. They weren't successful. There's a group in Europe that was able to do that. And that's almost amazing that they have a very big dish. I think it's something like an 18-meter dish. So it's a pretty good size ex-government surplus dish that they've restored for their use. But they do pulsar work and, excuse me, all kinds of stuff like that. So they've been selected by NASA. NASA was put out a memo for private parties that might be interested in helping NASA track the Artemis mission. And the DSES group was one of the ones that was picked. And so they're actively trying to set up the system so that they'll be able to track the signal from the spacecraft and mainly the Doppler shift. Because by Doppler shift, then the trajectory and so forth can be calculated by NASA. But in any case, okay. Well, Ted has the information, so I'm not as up on it. I just became a member last year, But anyway, it's an interesting group. They have a website if you're interested in looking at it and some of the things that they do. And but anyway, so that got me interested in perhaps maybe attempting to at least maybe pick up the carrier for Artemis. So anyway, Richard, if you're thinking of doing it, this is one possible way of doing it. I'm not sure if you'll have enough time to buy one of these things off of the Chinese website and get it in time for the launch, but something like this on a dish might do it. I don't know. Anyway, just thought I'd bring that up.
What size of antenna you need to receive?
Well, it's hard to say. It all depends on the signal that the space capsule will be transmitting. I think they generally use about like 20 watts, something in that range. And so if they've got any kind of directional antenna pointing towards Earth, you probably would not need too huge of a dish. I was thinking of using a 1.8 meter solid dish. Oh yeah, Ted's saying, yeah, NASA wanted 30 foot dishes or larger. So for the stations that they wanted to pick to officially sort of help them with their tracking. I'm not sure if you really need 30-foot dish to pick up just a carrier. If you're just interested in detecting the carrier of the capsule, you might be able to do it on a smaller dish. I know people with as little as 1 meter dish can pick up some of the probes that have landed on the moon. The Chinese have a lander that they put on the moon and so forth. And so people with as little as 1 meter can pick up the signal. So anyway, it'd just be something like an attempt, sort of to see if it's doable. And anyway, I just thought I'd bring that up since Richard kind of asked the question, and if he's going to try anything, well, good luck.
Well, brilliant. Thank you very much indeed. And
the Artemis mission, when they were looking for people, they were asking them to do carrier detect the Doppler shift, and they said you needed a 9 meter dish, but NASA are notoriously overestimating how biggest dish they actually need. So I would think a 2 or 3 meter dish will see something.
Okay.
So Michelle's new, or Michael's new dish that he's getting installed in his garden, that the 15 meter one he's putting in there, that will do the job quite well then.
Yes. I think to put it on the Eiffel Tower.
You just need a tracking mount now for it. That's always I always think about these large dishes. It's not the large dish that's the issue. It's finding some way to track with it, because what we're doing with our 1 meter size dishes is our drift scans, and they're essentially easy to mount. Just stick it in a single direction and move it by hand.
The only advantage here is that you know where to point at.
Yes.
And it's not necessarily an empty black part of the sky. You point it at the moon, and at least when the capsule comes around the back of the moon and comes back around either towards it or around it, you at least have one point in space that you know exactly that where it'll be. So
it doesn't move too fast either.
I think the moon itself, I think its actual motion is something like 0.5 degree an hour or something like that.
Yes.
So it's not very much. So if you were to track it, it would just pretty much be the sidereal time, which is about 15 degrees an hour or something like that. So tracking, if you want to track it for a long period of time. But again, since it's a bright light in the sky, and if you have a way of just looking at your dish and seeing where it's pointing, you can just move it and point it to the moon, and that's all you need to, kind of. So that's the only advantage in this case. But yeah. It's another interesting hobby. A lot of people that monitor some of these space probes regularly. People monitor some of the some of the Mars orbiting spacecraft. And they do that with fairly small dishes, not necessarily huge ones either. So some of the solar observatory probes also, people monitor those, and some of the probes that are out at Jupiter, they can monitor, at least detect the signal. I don't think they can demodulate and get any information out of it, but at least the carriers are detectable.
There is a French guy, rather young guy. He's well known. He has a 3-meter dish, and he makes such kind of thing. And if you are interested, he has a very nice software package called SatDam. And he has a lot of decoding stuff. And so you can, yes, on his side you have the list of all the satellite you can decode the data from this software. And I know that he did keep track of some Mars mission and things like that.
What's his site called?
Yeah, well, you know, if you can detect the carrier, that's one thing. If you need to decode the signal, and you're going to need a stronger signal. So that's the only difference between the two. It's easy to maybe just detect a faint waterfall carrier, but if you really want to get information out of it and decode it, then you're going to need a much stronger signal to be able to signal the noise to be able to decode it. So that's kind of the difference between the two. Just being satisfied that you're going to have a carrier that you detect and actually getting information out of it is quite a bit more difficult. Yeah.
Sorry, what did you say the website was called there?
I put on the SatDam.
Dam. See what you type in. Oh, SatDump. Okay.
Yeah, it's like a amateur satellite. AMSAT. AMSAT.
Okay. Well, what I'll do now is I'll formally bring the meeting to an end. By all means, keep talking. You don't have to shoot off, but as far as the video is concerned, I will terminate it. So thank you very much, everybody, for taking part, and see you on the 2nd of the 3rd.